use the fundamental theorem of calculus to evaluate if it exists some junk. Okay, so first of all, use the fundamental theorem of calculus. Well, why don't I just integrate this? Why do I have to use the fundamental theorem of calculus to do this? Here's the thing. Okay, you have two options, or you have a bunch of options really, but for your class, you have two options when you're given an integral. You can evaluate it using the definition of an integral, which is, as far as you're concerned, Riemann sums, which would be really annoying to do. Okay, or you can use fundamental theorem of calculus, which just says you can use antiderivatives to evaluate your integral. Let's use the latter, because it's a hell of a lot easier to use fundamental theorem of calculus. Just so that you know, it didn't happen in that order. It wasn't Riemann sums defined, and then later we found fundamental theorem of calculus. Fundamental theorem of calculus came first, and then Riemann sums came like 150 years later or something like that. We had a different idea of integration before fundamental theorem of calculus, but the formal, nice, pretty thing you know today as Riemann sums came much after fundamental theorem of calculus. Riemann wasn't even alive at fundamental theorem of calculus, I think. You can check that though. Okay, so what does it mean to say use fundamental theorem of calculus? We'll talk about that. It says use antiderivatives. Don't use the definition of integral like an idiot. Just joking. Okay. So integral from 0 to 1 of this junk is integral of 0 to 1 of this junk. What the hell happened here? Oh, snap. This x root x turned into an x to the 3/2, because this is x to the 1/2 times x to the 1 over 1. So you can add those puppies. That gives you x to the 3/2. Okay, sweet. So now we need an antiderivative of this guy here. That's not too bad. We can manage that. Let's see. What's an antiderivative of 10? 10x will do, because if I take the derivative of 10x, I get back 10. And this one, if I take the derivative, okay, forget the constants for right now. Just look at x to the 5/2. If I compute the derivative of that, I get 5/2 x to the 3/2. The x to the 3/2 is great, but the 5 over 2 in front sucks. That's why I have 2 over 5 here, which is going to cancel off the 5 over 2 that comes down when I take the derivative. This here, if you take the derivative of the whole thing, you're going to get back this part here. Okay, and that's always the test if you found a proper antiderivatives. Does this thing give back this thing when you take its derivative? Now there's no constants here. Don't worry about the constants. When you have a definite integral, it makes no difference whether you add the constants or not. You could add a plus c inside this square bracket, but when you do minus, you're going to subtract off the plus c that you added on, so it makes no difference. Don't bother including it. Only include the plus c when you're doing indefinite integrals. All right, so now I have to, according to this, I plug in the 1 into my antiderivative, and then I subtract the same antiderivative, but plugging in 0. And then you see what you get whenever you get your answer. So 10 times 1, I have no idea how to do that. If someone has a calculator, that would be really helpful. 1 to the 5/2, no clue. Need some help. 10 times 0. I know none of these calculations. I have no idea how to do this stuff here. Let's just pretend this is 0. Okay, this is some stuff. 2 times 1 over 5. That's just 2/5. 10 times 1 is just 10. I lied. I knew those. Don't get mad at me. 10 plus 2/5 is this. I just did some fraction stuff. You can do some fraction stuff. Check it out. See, make sure it works for you. Oh, I even made these blue animations here, and I forgot to do them. Well, there you go. There's the blue animation. That's so much more satisfying. Okay, hope that helps. As always, let me know if you have any questions. Email me, Facebook me, text me if you're researched me and found my number. Yeah, until next time. Peace.